Hi, everybody. Good morning. If you are in USA, and if you are in China, good evening. Welcome to this plenary panel from IEEE Services Congress. And on behalf of IEEE Services Congress and IEEE Digital Health, we welcome you this exciting plenary panel. And this panel, the theme is Future of Digital Health. And for organizing this panel, we got a lot of help from NIH, particularly NIH Director Dana. She helped us to bring all of the renowned professors and the project leader to talk about the future of digital health, and particularly we'll hear about their research and some future direction. So now I'd like to pass it to Dana. She will talk about a few words, and then Simin will be chairing the session. Thank you.
Thanks, Iqbal. So I'm Dana Wolf-Hughes, and I'm a program director in the Risk Factor Assessment Branch at the National Cancer Institute. And when Iqbal and I connected about this conference, one of the things that he asked was, what's going on at NIH that's innovative in digital health? And the first thing that came to my mind was this network that I've been working on for the past few years called the Intensive Longitudinal Health Behaviors Network, which has the goal of furthering our understanding of health behavioral theories by using new innovative technologies in the digital health space. And across these sites that we have funded over the past 3 years, we have a range of health behaviors, from mental health disorders to physical activity and sedentary behavior to substance abuse. But what we are seeing is that there are similar challenges that all of these investigators are facing for assessment of intensive longitudinal data. And so I'm going to turn this over to Simin, who is going to introduce the panel and talk more about the network.
Hello, everyone. Welcome to our section. I'm here to introduce to you some of the amazing work that my colleagues are doing in the Intensive Longitudinal Health Behavior Network. They will tell you and share their perspectives on why digital health measures are critical for understanding health behaviors, such as trying to increase people's levels of physical activity, mental health, quality of sleep, reducing sedentary behavior, smoking, drug use, alcohol use, suicidal behavior, and thoughts. These are all some of the health behaviors studied by the 7 UO1 studies in the network. To understand why it takes a whole team of people from different disciplines to understand within-person changes in health behavior well, here's a snapshot of the 7 studies. So basically, most of the studies are collecting phone-based sensing and wristband sensing data continuously. So in the first column, we have studies that last 6 months to some that last 36 months, 48 months. So if you collect digital health measures from human participants over that span of time, you can probably appreciate that there are a lot of human factors and a lot of engineering and other challenges that we'll have to take into consideration to do this well. So some of the amazing technologies and data types that we have, including ecological momentary assessments, trying to get people's digital health measures as they are in their natural environment, location data, accelerometry, physiological data, video images, and phone usage data. And we also have a website that I'm shamelessly putting on here. Check us out. Some of the tools and resources developed by members of the network basically can be accessed on the website, including programs and apps to get people to wear it, helping people visualize health measures, and then to pay participants. So here's the order of the speakers. So we have already heard from Dana Wolf-Hughes, and she will have another talk at 12:30 in another section, CDH 14. And then next, we'll have Stephen Intilli from Northeastern University talking about integrating sensor data into intensive longitudinal studies, followed by Donna Spush-Metz from University of Southern California telling us about participant engagement. And then we have Misha Powell, also from Northeastern University, talking about the modeling aspects of things. And finally, we have Justin Baker from McLean Hospital, sharing his perspectives on clinical applications and impact of intensive longitudinal assessments. Without further ado, let's go to our first speaker, Stephen.
Hello, everyone, and I'm pleased to be here. I'm going to talk about some challenges of interpreting and integrating sensor data into intensive longitudinal health studies to give you a sense of the type of challenges and problems and opportunities that we're working with. So the takeaway of what I'm going to say is that we have learned some lessons from the time study that I'm going to describe, and they are that we have incredible opportunities to collect longitudinal data on health-related behaviors, states, and contexts from mobiles by combining passive measurement and temporally dense self-report. But humans are messy and data are messy. And so we need better summarization algorithms, multimodal sensor fusion for interpreting the data, and visualization tools. And so there's a lot of work for you engineers to do, and I think we want you to join us. So the study I'm talking about is the time study. It's part of the ILHBN network that these other projects are a part of. It was funded by the NHLBI. My collaborator, Genevieve Dutton, is at USC, and I'm at Northeastern University. The time study is on temporal influences on movement and exercise. And what we're really trying to do is use intensive longitudinal data to study behavior. We want to look at the continuum of behavior change from adoption to maintenance and understand how reflective behaviors and reactive behaviors interact as people switch from adoption to maintenance back to adoption. So we want to understand health behavior change theory, but we want to do it by using very temporally dense information about activity. That's the intensive longitudinal data part. And so if we get data from self-report, we get data from sensors, we want to be able to predict a behavior event that might be happening in the future, something like a lapse in behavior. What triggers a lapse in a particular type of behavior, like getting less physical activity or becoming more sedentary? So study our population are emerging adults, 18 to 29. They use their phones a lot. Our inclusion criteria are that they're just doing physical activity or intend to. And they've been recruited from Southern California, but also nationally. And an interesting thing is the entire study is remote. So there's no face-to-face interaction with researchers. And that means they're a little bit more likely to just kind of do whatever they're going to do with their mobile devices. And then we're looking at a year of data from these folks, 250 people with passive sensing self-report. The self-report is coming from a smartphone and a smartwatch. In both cases, they're getting prompted with EMA, prompting like questions, what happened before how are you feeling before the beep went off? And then also some context-sensitive EMA based on sensing. And on the smartwatch, it's what we call micro EMA, very quick questions. I popped one up earlier that you can look at in a glance and essentially answer. And we're trying to get at reflective factors, things like feelings of control and stress, but also reactive factors like location and the phone use and transportation. On passive sensing, we're collecting as much as we can, raw accelerometer data, location data, phone and watch use, and then we need to interpret those data to get at physical activity, sedentary behavior, and sleep, the health outcomes that we care about, and then look for transitions between episodes to lapses. And so that's what the study is about. With self-report, we have two types. We have standard EMA on a phone, just popping up questions, where we interrupt less and ask more, but we also have what we call micro EMA, which is where we pop up these very simple questions on the watch and we interrupt more and ask less. And the end result of this is that we're getting 24/7, 365 temporally dense behavior from these individuals. It's a lot of data. And the details of this don't matter, just to say that there's a lot of different types. There's EMA from the phone and micro EMA from the watch and data during sleep and data during wake. Lots of different types of data. And it's very dense. It's a lot of it per individual. And now what? That's really the question. Do we trust it? Because now we want to start using it for analysis. So I want to highlight a few things as the type of thing you have to do when you work with this type of data. So first off, we need simple summaries of some sort, ideally device independent ones. What we use for this to get a sense of the motion is something called Monitor Independent Movement Summary MIMS units. It's an algorithm that my group developed to allow us to use different types of devices with different sampling rates and dynamic ranges and just get an overall summary of the motion and not have to worry so much if there's a small change in one device to another. So why do we want to do this? Well, if you take a commercial device like a Fitbit, you may get things out of it like steps, but you're not necessarily getting a total movement measure. There's a proprietary algorithm there that's processing the data for you. You can also take research-based devices and develop algorithms, things like the actigraph, but there's a proprietary algorithm that gives you this count measure, or algorithms like the ENMO algorithm, which was used in the UK Biobank study, but that was developed for a specific device. So the MIMS unit algorithm is really designed so that you can switch across devices and hopefully be able to compare across different devices, and it's open source, so there's not proprietary issues. So just very quickly, in other cases, if you have an 80 hertz device plus or minus Hg measuring motion, and a 40 hertz device plus or minus 2G measuring motion, in these types of studies, you ideally want to be able to compare those two. And so in this case, we did some work just doing some testing with different devices with this algorithm to make sure we could take a signal, interpolate it, extrapolate it to different dynamic ranges, and then filter it so it's focused on the human motion that we most care about. And when we did that with a variety of different devices, a variety of different sampling rates and dynamic ranges, on the right here, you can see the coefficient of variation lowers better. So the MIMS unit, it does a little bit better than actigraph counts or the ENMO algorithm in terms of allowing us to compare across devices. So this is an open source, relatively straightforward algorithm for getting you a motion summary. It's available for others to use, and others in the network are using it. So the MIMS unit's a start for us to start to say, how do we understand this data that we get? But it's a really simple summary. And there are problems with wrist-based sensing that we know about, things like gesturing and bicycling, where your arms don't move, but you're exercising a lot, or where your arms move differently if you're carrying things versus not, and determining the difference between sleep, sedentary, and non-wear types of behaviors, and then just missing data generally. So what we really need are more sophisticated algorithms, not just to summarize, but to explicitly detect physical activity types, sedentary behaviors, sleep, and sensor non-wear. So when we start to do this, one initial challenge is just data volume. And to give you a sense, in our study, we have quite a bit more data to still collect. People are in the study now, but we have 35,000 days of data, 2 terabytes approximately. When we run stuff, we really have to do it on a cluster with 50 machines, 20 CPUs each. That requires sort of half a day of work. And all of that, we can do it, but the computation and data visualization gets a little bit messy. The bigger challenge is that we have to it's dangerous to aggregate all this data before you really trust it. And so it's insightful to look at some data from some individuals. So here's MIMS unit data for per day for an individual. And what you see here is the blue lines should go all the way up to the red line. That would be 24 hours of data, but there's missing data. So there's places where we can't compute the MIMS unit because we don't have the raw data. So expected would be all like total blue, right? It goes all the way up to the red. But real world is there's missing data of various forms, and we have to try to understand why. So here are 2 relatively compliant participants. They're doing what we're asking them to do for the most part, but there's still a fair amount of missing data. Like it can be a couple hours a day. And we have to understand before we start using this data, is it missing at random or is something else going on? Here's 2 more or less compliant participants. And you can see there are some cases large chunks of missing data, some cases many hours per day. And some of these we know are from tech issues from Google, Fossil Watch, from our software. Others are smaller periods where participants are in non-compliance or large periods sometimes. And it's tricky to tease all this apart, but it's really necessary for us to be able to do it in order for us to be able to do the data cleaning, to use the data the way we want. So we can look at not just can we compute MIMS units, but what are the values we get? So the bottom here, you can see darker is more activity, lighter is less. And some obvious patterns of activity start to become apparent. So you can see where the person was sleeping roughly, right? But there are other patterns that we might like to see that we don't necessarily see, like weekend pattern behaviors or people who go to the gym, every single day. And they don't necessarily jump out at you, right? So we want to understand why. That needs exploration. Now we can start to take this stuff and then compare it to population norms. So the MIMS unit algorithm has been run across the NHANES data, and we took population norms from that for age and gender and started looking at comparisons for some of our subjects in our study. Here you have one The red is where we just did a very simple type of interpolation. The blue is the actual value, and you can see 10th percentile, 50 percentile, and 90 percentile from the NHANES study. And this person is not particularly active relative to what you might expect. So are these low values because this person's just sedentary, or because of the pandemic, or because of some other issue? Here are two other people. You can see they're also fairly sedentary. So those folks that we've looked at so far, we have a lot of people who are more sedentary than we'd expect. So we're trying to figure out, why is that the case? Here are some people where there's a bit more activity, but a fair amount of missing data in many cases. Right. So this is the type of problem you have to deal with when you're trying to deal with what we think is very promising types of data, but also they raise a lot of challenges for engineers. So even for this simple summary, the missing data is a challenge. But what about if we want to differentiate sleep, wear, non-wear, and use supervised learning algorithms to do that? We have an algorithm we call SWAN. It was validated on lab data with polysomnography and motion sensors, and it works pretty well on that data. But let's take a look at what happens when we run that on some individuals. So here's an output from that. The bottom is midnight, and then it kind of goes up through the day. And you can see sleep, wear, non-wear. So pretty much, yeah, the person goes to sleep about midnight, and then they sleep until about what you'd expect, and then they get up and they go about their day. There's a little bit of missing data, but it mostly looks like it makes sense. Here are two people where you can see clearly differences in global patterns. So the person on the bottom, they go to sleep a little earlier, and they get up a little earlier. The person on the top goes to sleep a little bit later. But here you can start to see a little bit more missing data, a little bit more chaos in the data at certain points, right? And we want to understand what is going on in these types of situations. So the major patterns are visible, but is it good enough? And if you think about sleep researchers, 20 minutes a night might be clinically relevant. So if the algorithm is making just a little bit of a mistake, even if it gets the global trends, is that enough to work with? So here's a less compliant participant and a very messy data set, type of data you sometimes see. And one of the reasons we get this is because the algorithm was developed with relatively clean lab data, not this type of stuff. And the missing data can then violate some of the assumptions of the algorithm. And we also have things going on like we prompt on the watch, or the watch vibrates, and that can cause motion to be detected on the watch, which then can make an algorithm that's assuming that non-motion is non-wear of that particular sensor. So there's a lot of tricky issues here that come up when you start really looking at the data. And the solution to this ultimately is going to be to try to use sensor fusion to help clean and interpret the data, not just rely on one source like accelerometer data. So here is some sleep data from an individual. What you're seeing here is the orientation of the sensor over time. And the part that's highlighted in the yellow, that's sleep. It's a very typical looking pattern where somebody is sleeping and then rotates their arm around after some amount of time. The rest of the period where looks like there's a lot of activity is where there's actual motion. But what also this yellow is highlighting is the time that the person self-reported that they were sleeping. So what's clear is they definitely weren't. Our algorithms detect that they're not sleeping at some of these times, but the little red dots that you see up near the top, those are where they're interacting with their phone. So by looking at when they're interacting with their phone, we can actually determine if they're interacting with their phone, they're definitely not asleep. And so we can determine that their self-report has a bit of an issue. So what we're doing now is we're trying to combine these different data sources to clean up the data. We can't rely on the self-report. We can't rely on the algorithm. So essentially, you can't rely on anything just on their own. But together, things start to be able to make more sense. Here you see a situation where there's non-wear followed by sleep, which is actually tricky for the algorithms. And then there's some reported period where they said they were going to be asleep, but they're actually awake, which the algorithms can actually detect, and there's additional evidence from the phone being used. And this last example here is a bit of a pretty tricky one. You have unusual behavior. The person is sleeping in the middle of the day, plus confusing activity, and you have non-wear next to the sleep where you have data, you have missing data, and lots of complicated stuff going on here. And this confuses the algorithms quite a bit. And what do we do in these sorts of situations? So these are the types of things we're dealing with, and I want to leave you with just a couple lessons learned. So one, is critical to be looking at this data, and we need less clunky tools to do that. We have huge amounts of data, and we have to summarize it, but we need to do it carefully, and we need to do it with high performance computing. The data have a lot of missingness. Sensor limitations cause some, participant non-compliant causes some, consumer technology causes some, And even the code that the researchers write can sometimes cause some. And interpreting all of this and dealing with it is very tricky. The machine learning algorithms that we have are trained on lab data, and they work great on that often, but you have to treat them with a little bit of suspicion when you take them to this real world data. And ultimately, to solve that problem, we have to combine data sources to really get the best interpretation. And that's where you come in. As the engineering community, we want more engineers involved in trying to figure out not just how to do this stuff in the lab with really clean data, really sort of straightforward, simple signal processing, but rather to help us deal with some of the lessons that we're learning here from the time study, which sort of coming back to where I started, there are these incredible opportunities, getting this really, really unique, interesting, dense, temporally dense data set that has both passive and continuous measurements and temporally dense self-report. They're indicating some of the things they're doing many times a day. But the data's messy, the human behavior is messy, and we need better summarization algorithms, multimodal sensor fusion, and visualization tools. So I'm ending there. Donna's up now, and we'll be back later for questions. Thank you.
Thank you, Stephen. That was great. And I'm going to use a lot of that in my talk, which is about engagement with this data collection. First, before I go any further, though, I need to thank my team. None of this could happen without the amazing group of researchers from across the United States that I get to work with. Benjamin Marlin, Pedrag Klajna, Inbal Nahumshani, Eric Heckler, Daniel Rivera, Michel Pavel, who's going to be speaking next, Natalie Golajewski, Mohamed El Mistri, and Stephen De La Torre. Thank you for your brilliance. And my funders, NIH, NCI, NSF. Thank you so much. So as outline of my talk, first I'm going to talk to you about our project, which is Heart Steps, which is a micro-randomized trial. And then I'm going to talk to you about engagement with mHealth interventions and how that works. And then we'll try and better define engagement. And then for the most important part of my talk, I'm going to show you my dogs. So Heart Steps. Heart Steps is a micro-randomized trial of a multi-component, multi-timescale adaptive mHealth intervention for physical activity. Those are a lot of words, and I'll explain them. First of all, we're getting data from about 80 people for a year. And the primary aims of this research are the proximal ones, are to understand timing and messaging in context for specific people, what works and what doesn't work to get people more active. And the distal one is to increase walking and decrease sedentary behavior in adult patients with stage 1 hypertension and otherwise healthy adults with obesity. Heart Steps gives us a robust platform, which I'm going to show you, for advancing behavioral theories and models. And it focuses on a couple of key theoretical elements. And there are so many theories in behavior. We picked a few that we thought had the best chance of describing and predicting behavior. Self-determination theory, goal-setting theory, and the mechanisms of change would be, of behavior change would be, do people set goals? Do they plan? Do the cues to action that we're giving them help? Are they motivated? Do they feel like they can make behavior changes? Is physical activity even salient for them? And do they feel supported? So a micro-randomized trial, just to a refresher, is we randomize each participant between intervention options at each decision point. A person may be randomized hundreds or thousands of times, multiple times a day. These are like sequential or full factorial designs, and it's also an extension of A/B testing and single case designs. We can explore through ongoing modeling which information is pertinent, what contributes to the explanation and prediction of behavior of physical activity. What measures can we drop? Which new measures do you need? We'll talk about that in a minute. But when you're doing mobile health, when you're doing any kind of research, the real estate for taking measures is limited, right? This is Heart Steps, so just showing it to you. This is our dashboard. And these are the measures that we're getting. So baseline, a bunch of measures, then weekly, barriers, and we take EMA, barriers and facilitators of physical activity. And then daily, we get the temperature, the weather, and a daily ecological momentary assessment, EMA, that's questions asked the participants on their phones. We ask them about stress. all sorts of other things. During the day, we're constantly getting GPS location, not fine-grained, but are they at home, are they at work, or are they elsewhere? And per minute, we're getting steps and active minutes as well as inactivity from the Fitbit. So this is an example. Let's say we're going to randomize people to a walking suggestion 5 times a day. The times are chosen by the participant, and they're randomized according to a very clever probability. And they're randomized to no intervention or intervention, and they're randomized, weighted so that they're more likely not to get an intervention, because it's 5 times a day and we don't want to drive them nuts. And if they do get an intervention, the intervention is a message pulled from a library of messages. They're based on participants' current, the choices are based on participants' current context, and the messages are all theory-based. And there's a similar pattern for anti-sedentary. Now, this is data from our ongoing study. And what we did was we divided it up to participants that have at least 8 weeks of data, but had withdrawn from the study by July 14th, versus participants with at least 8 weeks of data that are still enrolled in the study as of July 14th. And this is app views per week, just averaged. How many times did they open the app? And you can see that for the people who dropped out, that goes way down. It even started lower. And for the people that are still in the study, it's gone down, but it's holding steady at a level that is pretty much where this group started. So that's informative. And here's another way of thinking engagement. This is the EMA, or the questions on the phone, the completion per week, again, divided by people that dropped out by July 14th and for people that were still in. And this is a morning survey completions per week. So it's an average count. This is a count. And you can see that this really declines for the dropout people and stays pretty steady for the people that are still in the study. One more. This is average wear time, so average Fitbit wear time. And you can see that for the dropouts, it started about the same. So technology was interesting, but it dropped off really sharply. For the people still in the study, it has dropped a little bit, but not so steadily. So this is about engagement. What you can see is engagement with mHealth interventions is like trying to catch a falling star. This is from Baumel and et al. In JMIR, and this is percentages of people in a bunch of apps that opened the app from day 1 to day 30 out of the number of users who installed, and opened the app day 0. And you can see this pattern of decline to all the way to death. And this is a really interesting one, Scherer et al., also from JMIR. And the people here are split out for data available, how long they've been in the study, because this was a rolling admissions. 1 month, 2 months, 3 months, 4 months, 5 months, 6 months. So that also means that some of these people drop out. And you see that the people that have been in the study the longest and have stayed in, this is also mean days of usage of the app. This is a mental health app. Usage predicts staying in the study. Okay, but really, does non-completion or non-use mean non-engagement? What about, as Stephen talked about, failure of technology? Or what if in the case of our intervention, we set a goal of 10,000 steps a day, and the participant is reaching their goals and really kind of has learned the lesson and no longer needs the intervention and therefore disengages? Is that non-engagement? Or the participation has learned the relaxation technique that the app is teaching them? Or for smoking, the participant is feeling the urge to smoke less or actually quit, and therefore doesn't use the app anymore. Participants, this will say, can engage cognitively with the app's content or with the intervention without engaging behaviorally with the app. So the question is, if we're trying to understand engagement, are we asking the right questions? What do we actually mean by engagement? So Cole Lewis outlined this. This is a good start. Little e is engagement with the digital behavior change intervention. So engagement with the thing, the app, the Fitbit, whatevs, and engagement with the behavior change technique. So this would be, in our case, Are you using the Heart Steps app and wearing the Fitbit? And are you actually increasing your physical activity? Or increasing, that would be big E, increasing physical activity. And engagement with the behavior change technique in our case would be, are you making plans in the app? Are you planning your physical activity? So that's one way to think about engagement, little e versus big E. But we've really been thinking about it for a long time, and this is really Imbal Nahishani's work and others. There are three aspects of engagement. Behavioral. Do you perform the task behaviorally? Do you actually go for a run or use the app or attend therapy? So that's the use of the app and the doing what the app is asking you to do, right? Then there's cognitive. Do you spend time thinking about the task? Do you engage in cognitive processing at all? And then there's affective. Do you like the task? Do you enjoy it? Do you feel attached or committed? And these three aspects of engagement, only behavioral really gets attention, and that's because it's kind of easy to measure, but I would argue that it's not as easy as people think. In mobile health, engagement has always equaled behavioral dimension. This is not true. Few attempts are made to measure as a more comprehensive construct, and this is where you, as the engineering community, come in. How do we measure it comprehensively? We don't know which dimensions of engagement are important in achieving specific ultimate outcome. So it might differ across outcomes. So a smoking intervention might need different things to engage their participants than a physical activity intervention. It might differ across populations, and we've definitely seen this. In a diet intervention, if I'm speaking with the Hispanic community or if I'm speaking with a white community, the kind of foods that we talk about and the kind of interfaces that I show them, even the colors in the app, have to be different to make sure that the population is interested. And it will surely differ over time. So as you saw this fall off in engagement, you can expect that engagement with an app is going to differ over time. People are going to need different things at different times. How do we make sure that we give them what they need when they need it? So a measurement of behavioral dimensions of engagement, that's a work in progress. How do we measure cognitive and affective aspects of engagement? And how can we understand how engagement fluctuates over time to decide when and how to re-engage an individual? So these are some behavioral measures of EMA. I'm not going to read all of these. You can read them yourself. But, it's engagement with the ecological momentary assessment, those questions. Engagement with the app, are you using it? And engagement with the device, like, are you wearing it? These are often data that's tossed or not in the back end of our interventions. It's not well built to capture this data and use it. Some cognitive measures of intervention might be self-reported burden, self-reported perception of interruption, differential reactions to different prompts, questions, intervention components, time spent with the content, and self-reported engagement in self-regulatory activities. But getting this ongoingly without interrupting everybody's processes and asking them a bunch of questions is kind of tough, except for these differential reactions and the time spent. We might be able to glean that without asking too many questions, or with asking the right questions at the right time, maybe something like what Stephen was showing you just on a watch real quick. And affective measures of engagement, maybe self-reported satisfaction, self-reported fatigue or burnout, self-reported irritation, contact with study staff, maybe, but we have no ground truth for this. Plus, it's all super cognitive. It's not about how I'm feeling about the app. It's about how I'm thinking about how I'm feeling. So hello, IEEE, there must be a way to get at this using smart sensing. And then really quickly about modeling to describe and predict engagement. I want to say what isn't measured isn't modeled. And engagement, if I showed you those graphs, it's a moving target and it often disappears. And particularly for the people it disappears for, those are the people that we want to understand. So we're kind of like ornithologists tracking a rare bird. Some of us think we've seen it. Maybe we've only seen a feather or a footprint. We don't understand its habitat and we don't understand its behavior. What matters? Where is the signal in the noise? Is it usage or access over time, response to prompts, types of questions that were answered versus those that are skipped? Some people, if you phrase your question the right way, people like to answer it often. People like to talk about themselves. But if you ask them the same question all the time and it's kind of dull and obvious that it's just for you, the researcher, you might lose people. Maybe it's aesthetics. Is it beautiful? Do you want to change it up and avoid boredom? Do you need to avoid boredom, or do you need to breed familiarity? Do I always want to see the same thing? How often do we need to change things up? Is humor important or dangerous? What makes for participant burden? The myth is that it's purely frequency or length of an ask. But what if it has to do with more with what's asked, or how it's asked, or how things look? And does the participant feel like the app gets to know them? Is that desirable, or is that actually spooky? So that's what I have to say. Those are the tasks I have for you as the IEEE community. Thank you. I'll stay in the backstage for questions. These are my pups, and I'm going to turn it over to Misha. Thank you so much.
Hello, my name is Misha Pavel. I'm at Northeastern University, and my focus of my talk is on developing of dynamical models of individuals in order to optimize interventions. And the emphasis is here on predictive models of individuals, and recently that's been termed digital twins. I will give a brief example of a physical system to develop the intuition, and then derive from that statistical learning combined with principle-based models is probably the best way for us to go. Behaviors are hard to change and easy to attain. Bad behaviors, but hard to get rid of them. There are many ways people try to deal with it. They put up signs that didn't work very well. They hired coaches, that was too expensive. So now we are focusing on technology that could potentially help us help people improve their behaviors. And this is the general framework of this approach, which Donna and Stephen addressed already to some extent. We monitor, we analyze the data, we try to figure out what would be the best intervention. And this is the topic of this talk. The general idea is that we have a person that's behaving, and in this case sedentary, and although there is a goal behavior, we don't know how to help them. Well, monitoring can help to some extent, but it's only limited and helps only some people. The idea is to develop intervention, maybe messages, maybe some more sophisticated intervention as the technology develops, that would maximize the opportunity for them to improve their behaviors. Now, when you want to control any system, cars, boats, and even thermostats in your home, you really need to understand the model of the device that you control. And this is very much engineering approach, and you should be very familiar with this approach. And so we introduced this notion of dynamical models of behaviors that we would like to develop. Now, this is not an easy task, but as Donna mentioned before in her beautiful talk, but the idea is to predict individual behaviors. Now, I on purpose used engagement curves from Gertler's work, and the idea is to try to anticipate how these curves come about. And one important point is these are averages over individuals, but we need to model an individual. And I can assure you that individuals do not have curves like this. They are more rugged and stepped, and it's just a proportion of individuals is declining over time. So how do we build these dynamic models that would optimize and perhaps in this case help maintain engagement? How to generate those interventions. So I'm going to give you a very quick physical example. Suppose you would like to understand how swinging works in a park, and we would like to, in this case, be able to answer questions like when to push, how much to push, so what's the force. On the left, we have features, the weight of the person, of the swinging person, the length of the swing, the force that's engaged, or maybe the age of the person or their mood, what have you. We don't know a priori what would influence the swing. Now, what we try to measure is the amplitude, the frequency, and the decline of the amplitude over time. So what do we do? In this age, in last decade or so, statistical learning became very popular. So we start with that. But then we might consider a little bit of domain knowledge. So we observe and measure many samples, extract features like length, mass, age, temperature, and measure outcome variables, which is the oscillation frequency or time between peaks, amplitude declines, zero crossings, whatever. So when we do that, we obtain a very interesting curve, which is a very nice fit, that the period is increasing linearly with the length, and that the length does not affect the decline of slope, neither does mass. You can see that these regression equations have very small value associated with the mass. Now, but when we look at the physics of the situation, we can write the equation. I'm not going to bother you, but these are just simple differential equation that's even further simplified by some linear approximation. And this is, for those of us who work with differential equations, just a standard linear, ordinary linear differential equations. And if we do it in discrete time, it's a difference equation. So once we have that, we can actually solve for these problems. So all we have to do is to fit the parameters with our machine learning or statistical fitting of the models. So when we modeling linear time invariant dynamic processes as as second course in engineering, you start with continuous differential equations, you have difference equations. But what I'm trying to get here at is the fact that these equations are actually mapped quite nicely into statistical models like autoregressive model and state space representation, which is another version of representing dynamic models, is very similar to dynamic structure equations. In fact, very, very closely related. So if we have this understanding, we can then go from the principles of physics to compute the difference equation, use the ARX model, which is the statistical version of the difference equations, and estimate parameters. Now, why would we do that if we have the physics? The reason is that there are a lot of things that actually in real life for a particular swing differ from another swing. For example, friction and other aspects that. So using this approach, we can go back to the IRX model, to polynomial decomposition, which engineers are very familiar with, and actually derive some aspects of the physics. And this is the goal of our approach for behaviors. Go from the statistical learning towards deriving principles. So we combine machine learning with domain knowledge principle-based models and to actually derive models for behavior. Now, let me give you an example that is related to what Dana was mentioning, having to do with heart steps. Basically, there are we selected two psychological principal processes. One is habituation, and that involves the process where you remind somebody, you send messages, and repetitively and constantly, and every couple of minutes or hours. And people become less sensitive to those messages. And you can see it in the first part of this graph. Then we reduce the frequency and people become more sensitive and actually respond to it. The second process is reinforcement learning. As we reinforce people for either by them having success in walking or by giving them points, we can increase their utility for behaviors and frequency and of behaviors. This is work of Lisa Gottsian and Eric Heckler, and it's a development of the model. So we take the habituation and interpret it as a gain control. We take the positive reinforcement as a convolution with leaky integrator, and when we put it all together, we get a model that is looks very large, but it does not have many parameters. And we can use that model to actually estimate the probability of walking of any particular day. And this is an example of for one person that where we use 4 inputs. External cues, that's the messages that we send them. Outcome expectancy, this is the available time that they have to actually perform the walk. The reinforcement that is given them in terms of points, and that we have to also include whether it's weekend or weekday. And this is a very interesting aspect that introduces periodicity in the behavior, which is actually useful in terms of looking at the analysis. So this model was used to then using machine learning with the constraints imposed by the model that I had shown you before, and we found quite nice correspondence. But I must say that this is just the beginning of this work, and we are trying to figure out more optimal ways to actually use these data to set our interventions to be in time and in its content to be maximally effective. And once we have this model, we can do that by a search. So the take-home message for this from this talk is that using models as well specified as we can, and principled models, or some people call it mechanistic models, use data more efficiently. They can generalize and be applied to individuals, of course, population and new context, but the individual focus is very important here. And this modeling also enables us to collect better data than during the next experiment. We can test whether this theory is robust and how sensitive it is to various variables. And that will enable us to optimize intervention, provide causal explanations, and discover new questions. So I'm going to end here, and I will be available for questions in a few minutes.
All right. Well, thank you, Misha. And my name is Justin Baker, and I'm very pleased to be with you today as part of this panel to talk about some of the work we're doing to try to apply the intensive longitudinal assessment approaches in the realm of mental health, where I think you can begin to see what kind of impact it may have on how we think about the future of digital health. So I'm at McLean Hospital and the Institute for Technology and Psychiatry. And just to begin, I'll mention my funding and the folks who are currently in my lab, as well as many of the collaborators and tools that we have used, in particular my co-PI of this project, Dr. Scott Rausch, who is also the president and chief psychiatrist at McLean Hospital. So how do we assess mental health? How do we assess that someone may be experiencing a serious mental health condition? And normally we think of this as looking at different biological variables and comparing people with the condition versus without the condition, so-called cases and controls. But of course, in many conditions, this is a complex relationship where there may be different kinds of caseness compared to one kind of control. Or we may have continua between having a disease or not having a disease. And moreover, we may have situations where multiple conditions may be expressed within the same individual. Now, traditionally in our group, we've looked at this by looking across biological scales, trying to understand what makes a case relative to a control at the genetic level, at the brain circuit level, all the way up to signs and symptoms and the syndromes that we see patients experiencing. So there's many different levels of spatiotemporal analysis, but often in this case, we're looking across thousands of individuals who may be expressing these conditions to make these inferences. Complicating matters in the assessment of mental health is that brains are changing over time. Many individuals will express their disease only as they develop. And moreover, once they have a condition, that condition is changing frequently. For instance, in bipolar disorder, where individuals can change between a manic episode and a depressive episode in relatively short periods of time. So at the heart of the challenge for us in the realm of assessing mental health is that training a clinician or a research assistant to assess someone's mental health can take months to years. Administration of an interview and scoring it can take hours. And even with all of that, it remains highly subjective with poor intertemporal and inter-rater reliability. And so over the course of our work, we've concluded that in-person dyadic interviews are really not ideally suited for capturing robust point estimates of how someone is expressing symptoms, especially when those symptoms are across multiple dimensions and need to be measured over time in the same individual in some way that's reliable at scale. And so another way of putting this is that today, mental health assessment is very human resource intensive, very expensive, and nonetheless unreliable. Another way I think will resonate with the previous talk is that today assessing mental health is mostly open loop. And where it needs to go is really to become much more closed loop. And so just to remind us, I think this audience will appreciate that a closed loop control system, such as ones related to latent construct models, often have a sensor layer that feeds into a feature extraction layer to inform whatever it may be that latent construct, and that motors and actuators can generate feedback that allows that model to be tested. I think it's worth noting that the brain is constantly using closed loop systems to gather information about the world using actual sensors, sensory systems that have been evolved to have optimal feature extraction, but that using movements, the brain can generate feedback to refine its own latent construct understanding. Also worth pointing out that clinicians are using some closed loop methods to hypothesis test and figure out what the person in front of them may be experiencing. But this is often done sporadically and inconsistently. And so what I'll emphasize today is that our work using intensive longitudinal assessment is essentially trying to apply a similar approach by putting actual sensors onto, or in some cases, using individuals' own devices to gather information about them as they move through periods of severe mental health conditions. In particular, our group is interested in using data from a variety of raw data sources, some of which you've heard about today, from surveys, audio and video, activity from watches and phones, as well as signals like location. And we're combining that also with data from MRI scans and the medical record to really look across these data types and use feature extraction methods that in some cases have already existed. In other cases, we've had to partner with colleagues in computer science to derive better feature extraction from some of the data types that prior to this work we weren't as invested in. And ultimately, we're trying to tie these different features to the latent psychiatric variables that we care most about, such as sleep, executive function, language, affect regulation, and stress sensitivity. So the study that I'll tell you about today is called the Bipolar and Longitudinal study. This is where we followed 100 individuals with either depression, bipolar disorder, or a psychotic condition for sometimes as long as 4 or 5 years. We track their self-reports, we track clinician evaluations with them, and we also compare that with objective measures of their sleep and activity as measured through watch, a wearable device such as this one, and from their phone. So each individual participant has all of these different types of data being collected simultaneously, and we're interested in looking at trajectories of change in the different measures. So as mentioned, we measure a number of different passive and active sensor and behaviors, so as reflected here. And then we're using those to map into a variety of latent constructs such as energy level, activity level, sleep, both perceived and measured, processing speed, the rate and quantity of their speech and movement, ultimately to derive some latent understanding of whether they're in a manic, psychotic, or depressive state. And I'll also just note here that we could just as easily, using the concept of this network, map into many of the other behaviors that the other research network partners were studying as part of their studies, in particular because the patients who we tend to follow often have many of these same comorbid conditions such as smoking, drug and alcohol use, suicidality, sleep problems, as well as changes in their physical activity and sedentary behavior. And by taking this approach, we can collect our data set with one set of questions in mind and still apply it to other related questions. Now, I'll just briefly note the conceptual framework that we used in trying to approach our data, which is that it's been notable that in depression and mania, people have very strong changes in their level of expressed movement and energy. And so we thought we would be able to take some simple notions of energy conservation from how you might think of a battery being charged and discharged. So you can imagine that while someone is sleeping, they're not moving as much. What if this is a period of charging their battery? And what if while they're awake, they're essentially discharging that stored energy in the movements that they use? So on the right, I'm showing conceptually how this might look, where there's essentially a level of high and low energy, which once it's reached by some sort of drift diffusion process would induce a change in state that would cause that individual to switch from more of a conservation strategy to a spend strategy. So for instance, as someone is waking up in the morning, they would switch from conserving to spending, and then as they reach the evening, they would switch from spending to conserving, and that this ability to balance local energy would allow someone to, or cause someone to have their sleep-wake behaviors. But then importantly, having a perfect balance of this is often not possible. You either have to you maybe up longer than you intended, or you may be getting less quality sleep than you intended. And so over time, there could plausibly be a global balance that's accumulated in someone's energy, where they either are too high or too low, such as at the end of a semester or at the after a long period without a vacation, individuals might switch into a conserved state to balance their energy better. And so we first studied this in college undergraduates who were undergoing their semesters. And you can see here that based on a simple model of how they might balance their energy, which we can derive from the activity bracelet that they're wearing, we see that the expected pattern is essentially there by design. But what's notable here is that over the course of their semester, we see that these college students show a suggestion that they're actually losing that global energy over time. And that if you look across their entire year, it appears as though during that winter recess, there's a recovery phase where on average, those individuals seem to get back that global energy balance to a place where they can maybe plausibly be in better state for approaching that spring semester. And so we took that approach and looked at individuals who had depression. And here I'm showing you just a single individual who had repeated episodes of depression and sleep changes throughout their time in the study. So just for orientation, on the x-axis here, you're seeing 700 days over which we followed this individual. And here so far, I'm showing you just the responses that she provided on a smartphone. So these are a number of questions that she received each day about that were the positive and negative domains. And here you can see them represented in colors down here and with a kind of an average positive and negative valence. And what you'll notice is that while the person started off the study in a positive mode, they switched into this dense negative mode for almost 100 days. And then you can see they switched back into a positive mode for an extended period and negative. So just right off the bat, we can see that this is a way that we can use intensive longitudinal assessment to even just begin seeing some of the typical patterns of what depression may look like. But then what's interesting is we can compare that against what we see in the clinical, with the more extensive and expensive clinical interviews, and see that her depression scores, in fact, do go up consistent with that negative period, persistent negative moods. And then importantly, we can compare this individual's activity patterns over time with these changing patterns in her subjective and the clinical assessed states. And what you'll notice is that there's up at the top, I'm showing you essentially the raw or slightly processed activity from her wearable bracelet. Here we've taken something similar to Stevens' sleep wear and non-wear algorithm to derive sleep and non-sleep times. And then from that, we can take an activity differential, essentially how much was she moving during the day compared with how much was she sleeping at night. And you'll notice that while she's in this negative mood state, her sleep is quite disrupted and it's occurring for a longer period of time. And yet there's also greater activity, lesser activity during the day, similar to maybe if you were experiencing a viral illness and you weren't as active during the day, despite getting long periods of sleep. So we can apply our energy model to this person's data and see that, well, if we assume basically that there's a simple homeostatic assumption, we can see that this person's sleep energy balance changes abruptly at this period of time when her sleep changes, as if it's essentially recovering from a latent energy balance. Now, again, this is at this point still a lot of modeling to be done in terms of refining the parameters of this model. But I could say that the concept is simply that we want to link up what changes we're seeing in subjective states and clinical assessed states with some of the objective features we can derive from the sensor data. And this is, I think, a striking example of each time that this individual goes into one of these dense negative mood states, we see something like that energy recovery function, which has led us to this concept that depression and mania potentially could be viewed as having an adaptive role for the organism from an energy conservation standpoint. And that we're looking to establish whether this theory holds up across our entire data set. But I think it's at least shows the potential of how one can begin linking subjective and objective data to more objectively assess mental health. And then one final example, here's sort of that cartoon example of bipolar disorder that I showed earlier, where you have periods of mania or depression. But we've been able to study individuals who have real life bipolar disorder and can see how all of these different data types, as well as those modeled energy parameters, come together in a real person who's experiencing these conditions, with the hope that we can really begin to close our own understanding in terms of iterating those models and getting a better handle on the factors that influence these changes. And so again, I think just to wrap up, the goal here is to really move towards computationally defined phenotypes in chronic psychiatric illness. And this is, I think, where we can move beyond some of these more cartoonish ways of thinking about the differences between mental health states towards something that is really reality-based and something that I think the engineering community as well as the clinical community need to collaborate closely on. So with that, I will wrap up and be happy to take questions with the rest of my colleagues.
Okay, so thank you everyone for your great talks. So I've compiled some questions for our speakers. So the first one is a question for Stephen and maybe also Donna. Yeah. So Stephen, you alluded to the fact that you're using self-report of sleep duration kind of as the ground truth, right? To verify the efficacy of your summary measure. So usually when I talk with my sort of engineering collaborators, and then we tell them that we collect self-reports, when they ask, how do you assess, how happy people feel? And we ask people how happy they are, and they would almost fall off the chair, right? So what is your take and Donna kind of even mentioned that, for some of the things that she's interested in, like cognitive and affective engagement, there is no ground truth. So what is your take on whether it is sensible at all to have any ground truth when you're collecting, digital health measures of health behaviors?
Well, there's a lot packed into that question, I guess. I think at some level, for some things, we don't have any way of detecting them automatically. So there is no other way to get the data other than to ask and to trust to some extent that the answer that you're getting is a good result. In our case, we're asking about some things that have that flavor, and we're also asking about other things where we can verify with a passive sensor what they're saying. And then we can look at that and say, where is there a disconnect, right? So we on one hand, we want to be able to use the self-report data and say, if this large group of people says this is when they're sleeping and this is when they're waking up, we'd like to be able to trust that so that we can improve the algorithms that try to automatically detect that and have more faith in them. And on the other hand, when we run the algorithms and we look at the data, we can see there are clearly times when they're misreporting. We know that people often misreport information, right? So this is the challenging part, right? And then you say, well, now I can, I have colleagues actually, and they frequently come to me and they say, I'm doing a study and I just want to take this wearable data and I want to throw it into my study and use it. And my response to them often is, but where are you going to get the ground truth that you need to understand if your interpretation of that data is what you think it is? And they sometimes think, well, that problem's a solved problem. Like the sensor will just tell me with certainty that they're sleeping or that they're doing this or that. And that's not, in my opinion, that's not a solved problem. I think everybody working on these projects realizes that there's a lot of work to do to figure out how to do that, and how to get the ground truth to prove that things work, I think is a tricky problem. I don't think there's a perfect answer other than trying to bring together as many different types of sources of information as you can and triangulate essentially to see if you can get to what you think the truth is.
I will build on that. That's a great answer, Stephen. And Stephen is talking about behaviors that we could see almost, I mean, we can see when people are sleeping. We can see when people are active. But often, and that's already really hard. Everybody lies, as that famous house used to say, or people don't know. But a lot of the behaviors that I'm interested in getting at, like how people feel about things, they often don't know or understand themselves. So how to get at that? I don't think we can discount self-report and what people say. And I think that indeed there's sometimes all we can do is ask. But I think that there are going to be ways to triangulate data, as Stephen says, that will help us get at the unseen, the things that we can't see, and the things that we as yet can't measure. So things like cognitive interviews, different ways of maybe not ground truthing, although I think ground truth is really important, but maybe grounding and then moving from there.
Yeah, I'll just also add that in our population, individuals who may have a psychotic condition, you couldn't necessarily ask them directly, are you psychotic? You as a clinician, how to triangulate, to ask certain questions that in total maybe are consistent with them experiencing a psychotic condition. But I think the same concept is true here, right? We're trying to see what we could, there may not be a ground truth, or there may be sort of more sort of semi-supervised approaches that we would use to infer at least coherent pictures, whether or not they're reflective of the truth. They may be practical, they may be useful, and that I think is really the goal here, is to use what we can to take the best from clinical and machine learning and so on, to try to take these methods and make them useful.
Mm-hmm. I have a follow-up question, and then we have question from the audience that I'll ask next. I think that may be one for Misha. So, but Justin, right? So you mentioned that you are using sort of machine learning type approaches to facilitate feature extraction and so forth. And of course, machine learning methods can also be helpful in terms of trying to reconstruct latent constructs, as for the dependent variables, right? As well as working out the mechanisms, right? Linking the predictors to the outcomes or dependent variables. So in your view, what are some ways that machine learning techniques and approaches can best be integrated with expert opinions from clinicians, clinical psychologists who can kind of work in synergistic ways?
Yeah, that's a great question. I think if I had to take one take home, which is, I think many times, I think in health technology, we think of prediction errors as sort of, we're just going to run our model on lots and lots of data and just go ahead and apply it in a new sample and see whether it works or not. I think that's the missed opportunity. I think we need to use longitudinal assessment to see if, let's come up with a model and then see whether it predicts something useful at the next time point, and really think about following individuals over time as the way of testing our models. Because I think there's huge opportunities there where you don't necessarily need a research infrastructure or a clinical infrastructure or anything to get really large numbers of people. I think you can follow even a few people over time, and with the right kind of machine learning approaches, develop models that continue to be increasingly predictive over time in those people. And I think, there's obviously ways of thinking about the transfer learning and making it more useful than just those individuals. But I think that's one way I would recommend folks really try to orient their approaches, is to follow people and generate prediction errors over time. But
yeah. So there's a really interesting question from the audience. Which parameters are more relevant for constructing personalized models? Is that maybe Misha, you want to take that one on, or maybe someone else?
Sure. First of all, I'd just like to comment on the previous question, which is, I think that we do not take advantage as much of all the information that we measure. So, for example, a priori, one wouldn't think that the gait parameters are relevant to cognition, but they are. And what I would propose is that we will be more careful about building these models and look at a convergence of different measures. Each of them is not very good in terms of statistics in estimating the internal states, but the fusion of those is often very much better and potentially useful both for the engagement and for the internal states of patients that Justin was talking about. Now, this is clearly related to the parameters, and here is an important distinction. When we doing machine learning, typically we try to collect as much data as we can, just pack it into the machine learning algorithm and see which ones come out relevant. That's a problem if the parameters are interrelated and potentially non-linearly related. And this is why I'm advocating introducing as much knowledge, external knowledge, as possible. Of course, if we don't know anything, then machine learning is the only way that our human civilization has worked for us 2,000 or 3,000 years. But if we do have knowledge, then we incorporate it and use the parameters that are relevant from that perspective. Now, interestingly, for the pendulum example, which is why I chose it, mass has very it does not have very important role in determining the frequency, and that's counterintuitive, because you would think heavier objects would swing slower. So this is where model is very useful, right? And both the machine learning and the principal models work to show that. So in general, it's combination of those two factors. If you don't know anything, you just have to do machine learning as we do, apply to big data. But otherwise, we use parameters that correspond to the processes that we think are delighted.
So I do want to press the panelists a little bit, bringing back to the question that the audience originally posted, right? That is, how do you personalize your model, right? Do you use data from the single individuals? Do you use data from the whole sample?
So
any ways to combine?
So let me answer that, and this is very important point that I didn't make as clearly as I wanted to. First of all, we absolutely need to individualize, because we don't diagnose population, we diagnose individuals. So this is absolutely critical. And for many areas, psychology, people have done individualized models. This individualizations these days related to digital twins, which I mentioned in. So the individualization comes from taking a model that seemed to work for populations and then train it for the individual data. If you have a model, then you can train much more efficiently. For a huge population with a lot of variability, you need huge number of sample points. But if you have a model with 5 parameters, you can take longitudinal data for one individual and come up with very good model.
Thank you, Misha. I think our section is coming to an end, 12:20. There's one more question from the audience about change point detection methods. So the audience say that if input data change too much, prediction won't work. Do you see a need for new change point detection methods? Does anyone want to comment on that quickly before we end the section?
I will, and it'll be really quick, and then Misha can take over, or anyone else. But it's not that we need new change point detection, it's that we need new ways of modeling. Because if we are getting incredible data that changes all the time, and that's the point. Change is not your enemy, it's your friend. Yes. But we have to learn how to model it. So and detection ain't going to cut it. Misha, to you.
And I can give you a very simple example. People try to find the point at which dementia sets in by taking a linear function, straight line, and then decline. Well, it turns out that if you actually do careful modeling, you find a change already 10 years prior to this change point. So even if you use change point, you have to model it. Is it abrupt or is it gradual? And that will determines how we approach this.
Terrific answer. Thank you so much, everyone. And thank you for the great answers, great talks. And let's end this section with the quote from Donna: "Change is our friend, not our enemy." So thank you so much, everyone, for taking the time to attend our section. Thank you.